How safe are the planes we fly in? I'll tell you about it in a minute.
Why are planes built on the edge of failure? This is the University of the Netherlands.
We have all played the all too familiar game of Jenga at one point or another in our lives. Taking that starting stack of blocks and carefully removing a block one at a time, seeing the tower get more and more unstable, until that final moment when someone takes a block and the tower topples. But Jenga is just a silly game. It couldn't possibly have anything in common with the design of an aircraft. Or could it? One of the basic truths of human achievement is that everything we make has the very real potential to break at any given moment. Your bike or car could break down during your daily commute. The building you are in now could suddenly collapse. Or during your next flight on an aircraft, the wing could catastrophically fail, causing the metaphorical tower of blocks to tumble. You might think that the obvious solution to this is to make the structure as strong and durable as possible, to in effect do our best to make it indestructible. This is precisely what we try to accomplish in the design of a flight data recorder, which you might often hear referred to as a black box, despite its bright orange color. This component is designed to survive a catastrophic failure of an aircraft, so that the data stored inside of it can be used to investigate such a tragic event. So why don't we just design all things in this manner? Well, it creates a problem. It becomes very heavy. This is a problem for aircraft. As the heavier an aircraft is, the more energy is required to make it fly, making it less efficient. This would require us to burn more fuel for a single flight, increasing the environmental impact of flying, as well as the cost of flying for the passengers. So aircraft designers actually want to do the opposite and reduce the weight as much as possible. Doing so has the consequence of making the aircraft potentially more flimsy and easier to break, just like removing the blocks from the tower. So we have to do this very, very carefully. In essence, we want to design on the edge of failure, the safe edge, that is. I mentioned that removing weight has a tendency to make an aircraft more flimsy, but how flimsy can it be? Let's look at an example. Many of you have likely taken a holiday and flown on an aircraft such as a Boeing 737. In such an aircraft, you have a part known as the fuselage, and that is this tube along here that the passengers sit inside. In a 737, this fuselage is about 3.5 meters wide. But how thick do you think the skin or the structural wall of that fuselage is? A few centimeters? Half a centimeter? Actually, it's even less than that at just under 1 millimeter, or approximately twice the thickness of one of your fingernails. Theoretically, we could make it even smaller, but this leads to some practical problems, such as the skin being so thin that it starts to cut through the fasteners that hold the aircraft together. Here you can see just how flimsy a 1 millimeter sheet of aluminum is. I can easily bend it and even permanently deform it and damage it. So you can imagine if you scale that up to the size of an aircraft, effectively we're flying around in a big pressurized metal balloon. So if an aircraft is as fragile as a balloon, then how can we prevent it from catastrophically failing? We have to start by accepting that failure is a process that occurs over time rather than a sudden event. What do I mean by that? Well, imagine the classes you are taking in school right now and stretch your imagination a little and pretend that you failed one of those courses. Was that failure sudden? Did it appear out of nowhere? It might feel that way, but that isn't quite the truth. That failure resulted from a buildup of mistakes in understanding over the duration of the course. That buildup of misunderstanding then reached a critical level that resulted in failure of the final exam. If we could somehow detect these misunderstandings early on, it could be possible to repair them and prevent the student from failing the course. In the context of an aircraft, we don't quite look for mistakes, but rather damages, such as cracks and dents. I can plot this in a simplified manner with the following graph that shows that damages could develop over time and grow to a critical size, causing complete failure. But we have one practical problem with this graph. Scientifically speaking, we can trace that graph back from the critical damage size all the way down to the smallest initial damage. Practically speaking, however, we are limited in how small a damage we can see by our inspection methods. So there is a threshold that should be placed and represented by a wall over top of this graph that hides what happens when the damage is smaller than this detection limit. What remains is the window of opportunity in terms of time from how much time passes between the damage becoming detectable and becoming critical. And we can use this window of opportunity to set up regular inspections to detect and repair any damages that may develop. In essence, we accept that the structure can fail, understand how that failure evolves over time, and prevent that failure by detecting and repairing damages through regular inspections. This design philosophy is referred to as damage tolerance, and you might be surprised by some of the damage scenarios designers have to consider. Take, for instance, this military transport aircraft, the C-130 Hercules. This aircraft is designed to transport military personnel in a level of comfort that might make you rethink complaining about your next economy flight. Because this little plastic box hanging on the inside of the C-130 aircraft is its toilet. But don't be too terrified. They were nice enough to provide a little privacy curtain for you. Now, this toilet creates a very unique failure process that is specific to the male-dominated demographics of most militaries and human behavioral factors. Men, especially macho military men, have a tendency to, well, pee while standing up. And if you combine that habit with the risk of turbulence while flying, you can imagine there could be a small spillage issue. And since urine is corrosive, it can lead to corrosion of the aluminum structure of the aircraft in the vicinity of the toilet. So indeed, people have to study how quickly urine corrodes aluminum. They have to do calculations, consider different types of urines, and almost certainly had to do tests to verify all of this in order to determine how often we need to inspect for possible corrosion damage around the toilet. Then it is some person's unfortunate job to inspect for and repair any such damages. Now, you might think to yourself, well, isn't that silly? Can't we just avoid the problem by simply getting the military personnel to sit while using the toilet? The reality is that human behavior is difficult to control. For instance, if you have ever flown on a plane, I would bet that there is a good chance that you have had at least one time a Coke on one of those flights. Coke, like urine in the previous example, is also highly corrosive, and it spills on the floor of aircraft all the time, causing similar corrosion issues. But even knowing that fact, I bet many of you will still want a Coke the next time you take a flight. Even though we can inspect for damage, what happens if a problem is missed? Aerospace engineers have a clever second line of defense for this scenario. We design obvious malfunctions into the failure process. What do I mean by this? I think it is best illustrated with an example. I imagine you will all agree with me that the engines of an aircraft are very important, and we certainly don't want them to fall off during a flight. So we need to carefully design the attachment between the engine and the aircraft wing to prevent this. One risk to this attachment is fatigue failure due to the repetitive use of the engine over the life of the aircraft. Sort of how you can break a paperclip by repeatedly bending it back and forth. So how can we mitigate this risk? Well, we do something very clever. We include a second redundant connection that is a little bit loose so that it is not loaded and thus not fatigued during normal operation. If the primary attachment breaks, this redundant attachment takes over. If the redundant attachment takes over, the engine will vibrate more than usual, which can be felt by the entire aircraft. This gives the passengers a fright, but gives the pilots a very clear signal that something is wrong and that they should land as soon as possible so the problem can be looked at and fixed. Now, I just explained how aircraft engines are designed not to fall off, but sometimes that is just what we want. You can think about this by considering what an engine is in its simplest terms. It is a controlled explosion. We mix fuel and air into the engine and ignite it, extracting the power of that explosion to move the aircraft forward and to power the systems on board. But what happens if we lose control of that engine? It has the potential to pull so hard on the aircraft that it could pull the wing off. And although that engine is indeed important to an aircraft, that aircraft can glide to a landing without its engines. But if the wing comes off, it cannot fly at all. So we actually purposely design the engine to fall off before it can pull the wing off. We started off by talking about the game of Jenga, where players try to remove individual blocks from a tower, one by one without causing the tower to topple. In a way, this is how we design aircraft structures. We remove weight wherever we can, bringing it as close to the edge of failure as we can without it actually being unsafe. And this is done in order to make the aircraft as efficient and sustainable as possible. That sounds risky and perhaps a little reckless, but in reality, it is not. That is because aerospace engineers do not play this game fairly. We have models that help us predict the consequence of every block that we remove. We have sensors and inspection methods that we use to carefully monitor the tower so that we can detect any small amount of instability or movement before it begins to topple. And we include redundant supports that can prevent the tower from completely falling over. That is how we safely design airplanes on the edge of failure. Thank you for listening.